Good afternoon. Today our topic is design of countercurrent flow packed absorption tower. So absorption operation we started in last few classes. Packed plate column absorption tower already discussed. So today's topic is packed tower design. So packed tower basically is a cylindrical column where the upflowing gas remains in contact with the downflowing liquid solvent throughout the packed material at every point of the packed bed. And various types of packing material we can use in the packed bed tower. So these are the various packing material shown which are industrially used. And in the packed bed tower, at the top of the tower there is a liquid distributor through which liquid solvent enter the column, and from the bottom of the tower through a nozzle gas enter the column. And there is a support grid on which the packing material is supported, and the gas moving upward and liquid moving downward, contacting between two phases takes place there. And after the mass transfer operation, the gas containing the solute after removal of absorption leave the tower from the outlet, and the liquid carrying with the solute leave the outlet of the column. So entering gas is rich in solute, leaving gas is diluted in solute concentration. On the other hand, in the liquid phase which is coming at the outlet is concentrated with the solute. Now, what are the various steps we need to consider for the design of a packed absorption column? First of all, we need to select a suitable solvent for a particular type of absorption operation. Now we have to select type of packing suitable from various types of packing materials shown. Now one important design parameter is the calculation of minimum solvent flow rate as well as actual solvent flow rate. Now column diameter, height of the column, these are two important parameters, and design of the liquid solvent distributor and redistributor if required. Now, along with these main design parameter, design of gas distributor, packing support, sail, nozzle, and column supports are also some design parameters for a particular absorption column. Now, there are some required data. Some data are required when we are going to design a absorption packed column. So these data are equilibrium data for a particular operation, then gas liquid flow rates, and the concentration of solute at the inlet and outlet or inlet and exit of the for the both gas as well as liquid phase. And two individual as well as overall volumetric mass transfer coefficients are two important mass transfer parameters we need to design the packed column. Okay. So now for step-by-step design of absorption column required the important database for equilibrium line and operating line. Now first of all we need to make a plot of equilibrium data, or from the equilibrium line from Henry's law equation y equals to mx on xy plot, where x represents the mole fraction of solute in the liquid phase and y represents the mole fraction of solute in gas phase. Now it can also be represented in terms of mole ratios, in terms of capital XY, where capital X represents the mole ratio of the solute in the liquid phase and capital Y represents the mole fraction of solute in the gas phase. Now, then operating line need to be drawn in the same xy plane, where 2 points of the operating line represents the two terminal condition of the gas and liquid flow rate. which are represented by x1 y1 and x2 y2, where x1 is the liquid solute concentration at the outlet of the liquid, y1 represents the solute concentration at the inlet of the liquid, and x2 y2 represent the top concentration of solute in gas phase and liquid phase. So they represent, x2 represent the outlet concentration of solute in the liquid phase, and y2 represents the outlet concentration of solute in the gas phase. Now, the operating line can be drawn by the material balance equation based on author of the column. So, this is the main equation, Gs into y1 minus y2 equals to Ls into x1 minus x2. In terms of mole fraction, if we want to write, it will be like that. Now, if you follow the equation, it is an equation of a straight line which passing through two important points x1 y1 and x2 y2 having a slope xs by gs, Ls by gs. Now, this relation indicates the relation between liquid and gas phase concentration at any level of the tower as a point P. Now, operating line of absorption column, always there may be a straight line or maybe a plot depending on the nature of plotting. That means if we make the plot based on mole ratios, it will be always a straight line. If we make the plot on mole fraction basis, it will be a curve. And always the operating line lie above the equilibrium line. Now, next design parameter, the minimum liquid gas ratio for absorber. As I told you that the gas in the absorption column design, the few parameters are fixed by the process requirement, which are the gas flow rate, the two terminal concentration of gases, and inlet concentration of solute for the solvent phase. But the solvent flow rate is a design parameter which is based on our choice or some consideration we can fix. And if we, as liquid flow rate is not fixed, so the outlet concentration of liquid, that is the x1, is also not fixed. Now here it is shown how we can calculate the minimum liquid flow rate from the equation of operating line and equation of equilibrium line. So from the diagram it is clear to us two type of nature of equilibrium line, may be straight or may be curved. Two type of curve is shown. So now how we can find out the minimum liquid flow rate. The operating line must pass through the point. If we follow the operating lines, then it will be clear to us the operating line must pass through point D. Okay. So, and it also pass through point ordinate y1. So these are fixed points. So now if we vary the liquid flow rate, the slope of the operating line will vary. It will be convergent to the equilibrium line or divergent with respect to the equilibrium line. So if we increase the liquid flow rate, we observe that the operating line slope becomes steeper. So it becomes divergent with respect to equilibrium line, and at the same time we observe that driving force for mass transfer increases, which is beneficial for the tower column. To the height of the column will decrease, but at the same time with increasing liquid flow rate, the outlet concentration of the solute also decreases, which becomes very difficult to recover in the next step. On the other hand, if we decrease the liquid flow rate, we observe that the exit composition of the liquid gradually increases. So it is beneficial with respect to the recovery step, but at the same time, driving force for mass transfer decreases for diffusion. So the absorption becomes more difficult. Less driving force means more contact time need to be provided. So the taller column required for the shape separation purpose. So in this way, if we go to decrease the liquid flow rate, we observe that there is a limiting condition for minimum liquid, that is termed as minimum liquid flow rate, which can be used for a particular absorption operation, which corresponds to operating line DM. This DM represents a condition of operating line when it becomes tangent with the equilibrium line or it touches the equilibrium line with respect to ordinate y1. So at this condition, the driving force for mass transfer becomes zero. At this condition, as mass transfer becomes zero, So the separation becomes very difficult and tower height requirement become infinite. So this is an inoperable condition for the tower. We need to operate the tower above this flow rate, and the concentration at the outlet of the tower will be more than the minimum liquid flow rate. So as the actual liquid flow rate, we have to take a value approximately 1.2 to 2 times of the minimum liquid flow rate, and then we can get a better result for outlet concentration. Thank you for today.